Thank you everyone for joining the talk. Today, myself, Sumedh, and Jesus, we're going to talk about optimizing Iceberg table layouts at scale. Little bit about my background. I work at LinkedIn, and I work on Openhouse, which is an open source control plane for managing Iceberg tables at scale. Been working on this problem statement for over 3.5 years, trying to take LinkedIn's exabyte scale data lake to Iceberg, a well-managed Iceberg offering with Openhouse. I'll give it to Jesus, who will introduce himself and kick us off.
All right, thanks, Sumit. Yeah, my name is Jesus. I'm part of Microsoft. I work on Fabric Data Warehouse, but when we did this collaboration, this work, I was part of Gray Systems Lab, GSL, which is the applied research group at Azure Data. So with that, let's get started. So if you've worked with Iceberg or other table formats for that matter, chances are you've run into some of these issues, right? Storage fragmentation, slow queries due to skew or small files, jobs that hit unexpected bottlenecks, and many others. And these aren't necessarily new type of problems, but in modern data lakes, they show up in much harder ways because now you have many engines, many users, and lots of concurrent jobs, all interacting with the same shared data sets and infrastructure, right? Adding multi-tenancy, adding unpredictable access patterns, and possibly other factors, and suddenly even what you consider simple problems become a constant challenge. Now, one solution to this is to try manual optimization. But soon you realize that since modern data lakes are so dynamic and complex, manual optimization just doesn't cut it. It doesn't scale. We can rely on someone hand optimizing partitions or compacting files on a schedule or anything along those lines. So what you need to do is moving towards autonomous data services, systems that are observant, predictive, and proactive, and will help you with these tasks. And in a broader sense, we laid out this type of vision for Azure Data a few years ago in the paper that is referenced in the slide. That vision applies across data infrastructure in general, not just lakes, but in this case, we want you to apply to data lakes specifically, right? So once you decide to go in that direction, the question is, where do we start? And together with our colleagues at LinkedIn, we decided to look into data layout optimization. So data layout issues, things like small files, skewed partitions, poor sort order, form a category of problems that degrade performance and increase costs in the lake. These are problems that show up both across cloud and on-prem environments, and they will compound as the systems scale, right? More data, more jobs, more churn. And that's why we thought that layout optimization was a strong area to begin applying these autonomous techniques, since the end results should have broad, measurable impact across the whole stack. So with that, this is what we're going to cover today. We'll start by looking at how the small file problem, that is one of the challenges within data layout optimization category, shows up in practice at LinkedIn. Then we'll introduce Autocomp, that is our automated compaction system. We'll share results from both real deployments at LinkedIn and synthetic benchmarks that we run to gain further insights. And finally, we'll talk about what's next and the broader challenges that we think are worth tackling. So with that, Sumedh, you want to take it away?
Thanks, Jesus. Yeah, so at LinkedIn, we are managing tens of thousands of Iceberg tables with Openhouse. I think last time I checked, it was about 50,000 tables. And we plan to grow to 100,000 tables by end of this year. So, and one of the things that we ran into when we were scaling our deployment was proliferation of small data files in Iceberg tables. This was not just impacting application reliability and performance, but given that we are using HDFS, it has limits on how many files a name node can host. We started hitting scalability bottlenecks on HDFS as well. So this motivated us to look into this problem statement. Now let's talk about the origination of the small files. Some of you might have already experienced it firsthand, but on the left side, it's a very simple Spark application. It's some data frame trying to write to an Iceberg table. Now, depending upon how you have configured your Spark session, there are bunch of configurations that can drastically change the way data gets laid out on your storage. Let's take that first example of shuffle partitions. You set it to 200, it will create 200 shuffle partitions, 200 tasks, 200 output files, irrespective of data size that you are trying to write. And this is pretty common when you're doing wide transformations like group by repartitioning. The second one is default parallelism. Now, we want to make everything embarrassingly parallel, but what this means is setting this to 100 would generate 100 output files, irrespective of data size. And we saw this in practice when somebody was trying to do a narrow transformation, which is just a mapper only writes, direct writes to storage, and they were trying to write 3 gigabytes of data with 1000 parallelism. What that means is the files were 3 megabytes in size. And then there were downstream implications of that. Finally, max partition bytes is another configuration in Spark that you can tune. What it allows you to do is it reads in smaller chunks. And then when time comes to write back those chunks, if the developer is not careful with the coalesce or repartitioning, then they would end up writing 64 megabyte files. And at LinkedIn, we have tried to normalize the file size to be about 512 megabytes so that we have a good trade-off between the performance of the queries and also the storage scalability that we are dealing with. Similarly, Iceberg table property also exposes this. So as you can see, there are a bunch of these knobs, and then the end user is expected to like make them work when they are actually writing some business application. So that was one of the scenarios we are seeing in origination. Now then, the other class of origination is coming from genuine use cases where, like for example, for streaming rights, you want to have very low ingestion latencies. But it's not practical to have like file size that are rightly sized at the time of writes. Similarly, Trino will make trade-offs. It'll have unpredictable number of files because it's trading off query efficiency comparing to making sure everything is right-sized. And finally, bringing Iceberg into your lakehouse will exacerbate your amount of storage footprint because Iceberg has its own write amplification because of versioning that it supports. But not all these small files are a mistake, right? Sometimes it's a tear-off. Most data engineers optimize for job success and runtime, which means they are like focused on getting their application done instead of like having to focus on the long-term health of their tables. Defaults. Spark says that we have certain defaults that for all the configurations that we looked at, but one size does not fit all. And finally, lack of visibility. So there's no good tooling built around a feedback loop between the writes done by the job and the downstream impact of those writes on table, storage, and query health. Devs often don't see the query pain much later, weeks or months, and can't trace it back to the right job that actually generated those small files. And there is rarely tooling built to understand the file size distribution, metadata growth, and when is the right time to do the compaction. So in the beginning, everything looks fine, right? Jobs are succeeding, dashboards are green, but under the surface, something is quietly building up, right? You don't notice it at first, just a few more files here and there, a couple of retries, timeouts, and then there is a thundering herd problem one day. Your query starts slowing down, they crawl, and next day they fail, and your costs are up, your tables are bloated. So when the original intent of the right job was to run as fast as they can, throw more partitions to the Spark so it can run faster, the impact of it is on cost, reliability, on performance. So what does Iceberg do to solve this problem? So Iceberg has this neat Spark action that allows you to rewrite data files. Basically, it's merging multiple small files into large files. We all know this process called compaction. But what Iceberg doesn't do today, and what we are trying to bridge that gap, is addressing some of these questions. So who's responsible for calling the rewrite data files API? Is it the writer job, or is it some background process? How much compute budget do you have available to do the compaction? What are the candidate tables for compaction and schedule when you are managing a data lakehouse which has 100,000 Iceberg tables, right? And if you are actually doing rewrite data files to do compaction, is that sufficient, or you could add a bit more to that whole process, like for example, sorting? So those are the kind of things that are still unanswered. and our work partially tries to answer them, and then there is a roadmap that we would like to discuss with the community. So with this context in mind, we framed this problem statement that how do we perform a cost-benefit analysis to select top K tables out of all the 100,000 tables that you have for compaction, ensuring that they fit within a fixed resource budget that you have dedicated to your compaction jobs. So we frame this as a multi-objective optimization problem, where we are trying to optimize multiple objectives, which often have conflicting goals. Cost and gain are two conflicting goals often. Sometimes if you want to get more gain, you have to pay more cost. But here, we want to maximize our gain in terms of reducing the small file count while minimizing the total cost of compaction. When you start framing the problem in this way, you come up with some kind of a selection criteria. And that's what we talk about in, like, how do you select the top K tables that you want to compact? And then you start looking at what are the trade-offs. Should I compact a table which is massive and has a lot of small files, but is very expensive to compact? Or should I compact a table which is small and hence cheap to compact? Or should I compact a table which has a high churn rate, which means like I have a writer which is churning data every day, and then if I compact it, my compaction efforts are undone immediately when the writer job runs next. Or table D, which is like not often queried, so I might get some storage benefits, but I may not see the same benefits on query performance gains. So it's about trade-offs, and that's why we framed it as a multi-objective optimization problem. And Autocomp is a solution to this problem, which we'll talk about next. So automatic compaction at scale was one of the goals that we intended to achieve in our first version. The code is open source. It's in this repo, github.com linked in Openhouse. And specifically for the first iteration of data layout optimization as part of Autocomp, we wanted to optimize these two objectives. We wanted to maximize the small file count reduction, and we wanted to minimize the cost of doing compaction. In terms of requirements, the way we saw how Autocomp should evolve is we wanted the functional requirements for Autocomp to work at a fine granularity. Now, I have been talking about top K tables, but it could be might as well top K table partitions. So you could rank table partitions and then like pick them for compaction. Then we wanted Autocomp to have a cost-aware compaction strategy, because going through all the tables and then compacting them would be really, really costly at scale. And finally, we wanted to make sure it runs on a periodic schedule. Yeah, so for the non-functional requirements, we wanted it to be extensible. So right now, we are just doing simple compaction, but our vision is to like extend it to do sorting, Z-ordering, all those other data layout optimizations when they make sense. And finally, like when you talk about this, when you treat something as an optimization problem and you have to deal with trade-offs, you want to be able to explain easily like how you're making decisions. We wanted to stay away from ML, using ML to have that answer, because we wanted some kind of an explainability. And hence we just went with some simple optimization algorithms that we have implemented. And of course, we wanted to build this in a cross-platform compatible way so that it's not just specific to Openhouse catalog, but can work with any other Iceberg catalog. So putting this Autocomp into an end-to-end workflow, we followed the framework OODA, which stands for Observe, Orient, Decide, and Act. So first, we observe all the candidates in the various table and table partition granularity. For each candidate, we'll pull statistics from Iceberg system tables and metrics that we collect as part of our Openhouse deployment. We orient these metrics, these statistics and candidates to calculate traits. And the traits are essentially, think of them as scores that we'll assign to each table or a table partition. And finally, when we have to decide it, we'll just rank all the tables with their scores and then pick top K to fit within our budget, our compute budget that we have allocated for compaction. And then we actually act on that compaction. We actually call that rewrite data file API, which is in the last step. And this feedback loop is very important because then this allows us to iterate dynamically as things change in your lakehouse, workloads change. This feedback loop allows us to be like a bit more dynamic. Putting this into how it's actually done. So on the left side, you see you have like hundreds of thousands of like Iceberg tables. They have their data, metadata, statistics. The first thing that we do is we compute two threads. So rewinding, we said we are trying to optimize the file count reduction objective and the compaction, maximize or minimize the compaction cost. So we estimate how much file counts we will reduce by compacting a certain table. And we also estimate how much cost it will be to compact those tables from a compute GB hour standpoint. Now, once we have both these traits, we normalize them because both of them have a different scale. So we normalize them on a single scale using a simple min-max normalization technique. And then we scalarize them to compute a score using weighted sum scalarization that allows us to compute a score for every candidate that we are dealing with. And finally, we have scores for every candidate. We rank them, we pick top K under the max compaction budget. So on the right side, you will see only those tables that are being picked for compaction. Moving on to the evaluation section, before I jump into the actual numbers that we have, so this is the system that is deployed at LinkedIn. This is called Openhouse. We've been working on this for over 3.5 years now. And Openhouse is that exposes that managed table API to the query engines so that any query engine like Spark, Trino, in future Flink can interface with. It is essentially a catalog implementation, another catalog implementation of Iceberg. But in addition to catalog, it essentially has some of the maintenance services that we want to run on a schedule so that our end users don't have to worry about them, end users who are adopting Iceberg and Openhouse. And on the left side, we have a bunch of like generic data management services like retention, replication of Iceberg tables, and DLO, which is what we are talking about today, that will allow us to like optimize the layout of the Iceberg tables. So we put Autocomp to work at LinkedIn sometime, I guess, in October last year. And okay, sounds good. So yeah, so we started looking at the data, and the way we visualized it was we said, okay, let's plot a file size distribution histogram. So on the x-axis, you will see the buckets are different file sizes, and on the y-axis, you will see how much percentage of files fall into those buckets. So the orange bar is before we had any kind of compaction. So as you can see, the file size distribution is heavily skewed towards small files, which are smaller than 128 megabytes. And then at some point, we ran into situations where some of the tables got into a really bloated state that I was talking about, and they could not, the queries would not complete. So we picked those tables, and we said that, okay, we're gonna take these tables because they are highly sensitive, and we're gonna run the rewrite data file API on schedule. That's what we call manual compaction. So as you can see, after 2 months of running manual compaction, we saw the dark blue bar, we saw the file size distribution change, and it started moving, shifting right, which is what we want. We wanted all of the file size to be closer to 512 megabytes. So we started seeing that distribution shift. Then in a month, we started observing even manual compaction, the results. And we saw that there was not much change in it. And why is that? Because we had a very predictable pattern for those tables. We didn't get much ROI by compacting the same tables on the same schedule. And that was, we had been doing, at LinkedIn, we have been doing compaction for, I don't know, more than 5 years now. And our algorithms have been, no, we have to compact all the tables at a certain fixed schedule. And we saw this, and we realized that, okay, that kind of a model doesn't really like get us the maximum ROI that we can leverage. And we had been thinking about auto compaction because we wanted to roll out auto compaction for not just those couple of tables, but across all the entire warehouse deployment. And when we deployed Autocomp in the 4th month, we started seeing even better shifting right on the distribution part. This is another way to look at the data. So this is over the last 12 months. X-axis is the months, and y-axis is the normalized values for file count and our deployment size, which is like in petabytes. So as you can see, before the 4th month, the rate at which our file count was growing was much faster than our deployment size. And the moment we started doing manual compaction, we started seeing some benefits of it. But the real benefit came when we enabled auto compaction. And you can see the drop in the 9th month between 8 and 10 on the auto compaction side. So the other impact of this is on storage file system operations. This results in how many file opens do you have on your storage as part of your query. And when we plot this again on the same scale of months of Openhouse deployments and comparing the manual and the auto compaction, you can see on the month 4, there is a drastic drop in the file system operations. Now, we were able to reason about it because that one gigantic table had tens of millions of files where the Spark job was trying to read them. And then you had the HDFS client timing out, doing retries, causing a thundering herd problem. And then there was a drastic drop. And the moment we started doing that, the compaction for just that table, it was manually identified as part of our on-call. We did the compaction, and then we saw a drastic drop. And we saw a similar trend with manual compaction. And we continue to see this. The file system operations, specifically around file access count or scanned files during your query, changes drastically as you do compaction. And it has impact on your storage costs, your storage reliability, and so on. Now, this is one of an interesting one because this is something we are still iterating on. So how does all this compaction at scale impact your workload metrics? So we picked a scan-heavy workload that runs daily, scans tens of petabytes of data, and we tried to plot this. And we see a very high correlation between workload characteristic for that particular workload and file count. And you see this sawtooth kind of like a sinusoidal wave because our compaction is not running daily. Our compaction is running at periodic boundaries. It is ranking tables that should be picked up for compaction, picking those top K tables, and then doing the compaction. So you see the normalized values for all these characteristics like file scanned, query cost, query time going up, and the moment compaction runs going down. So this is interesting observation, which we thought was interesting to share. But it's a really hard problem to explain the impact of compaction on the workload characteristics, and that's something we wanted to do, and that's where like Jesus is going to talk about how we simulated this in synthetic benchmarks and show the numbers.
Thanks, Sumit. Okay, I'll continue, and I will talk now about the evaluation using synthetic workloads. So like Sumit was saying, in addition to the real-world impact at linking, we also run synthetic benchmarks because there are things that are just hard to evaluate in production, right? Especially when there is a lot of interplay between systems, components, workloads, and so on. So what we did here is that we mirror a linking deployment running on Azure. So you can see there that you'll have your Spark and Iceberg deployment. We also deployed Openhouse on Kubernetes using the Terraform scripts that are provided by the project. And in order to run the workloads, what we use is LST Bench. So LST Bench is a benchmarking tool for table formats that we develop at Microsoft, and we integrated it with CAB. So CAB stands for Cloud Analytic Benchmark. What they did here is that they took a snow set that are a set of traces of cluster utilization of a Snowflake clusters. And then what they do is to mimic the load of those clusters using open benchmarks, in this case, TPCH. So we took that, we did that integration, and then the end result is that you can run diverse concurrent workloads in your, on your engine. You'll have, some of them are constant load, it could be like a dashboard. Some of them are periodic, like hourly jobs. You have short bursts, someone that goes to their laptop, their desktop, they want to run a few interactive queries, or also you can have these kind of large bursts, maintenance jobs like compaction. The data in this case for these experiments was stored in ADLS, that is the data lake offering of Azure. And one key takeaway here is that all these projects that you see there, everything that you see there is open source. So you can go out there and try it yourself. And I'm going to highlight the specific aspect that, again, was kind of more difficult, as Sumit was pointing out, to see at LinkedIn, right? That is query performance. So this is a kind of a busy slide, but let me walk you through it, okay? So in each of the charts, in the x-axis, what you see is the experiment time, right? So we are running the experiment for 5 hours. And what you see on the y-axis is execution time for the queries that were executed in that bucket. And you see basically it's a candlestick. You have like minimum, 25th percentile, median, 75th percentile, and max. That's what you see over there. Now, if we go horizontally, on the top you have read-only queries, so your selected statements, and at the bottom you have read-write queries, in this case, inserts and deletes. And then we go with the colors. Left-hand side, no compaction at all. In the middle, you have our Autocomp with the multi-objective optimization running at the table granularity with the top 10, so the K is fixed to 10. And then finally, on the right-hand side, you see a hybrid approach, so you'll run on tables and partitions, and the K is set to 500. So two important things, I think, to observe here is that obviously you can see after the second, third hour, execution times get faster as the experiment progresses when we're running compaction. But maybe even more importantly, the variance, you can see that it goes down, right? The size of that candlestick, which means that the performance is more predictable, which is something that end users really like from the system, right? So yeah, I mean, we have been discussing mostly compactions in terms of storage efficiency, but as you can see here, it has a clear and significant impact on query performance as well. And with that, let me move to kind of next steps and what we see as open challenges. So first of all, when we look only at Autocomp in isolation, Sumit was showing this slide, right? I think there are other factors that we can also take into account when we are making these decisions and these trade-offs between cost and gain, right? So things that we're looking at is, for instance, maximize query performance gain in terms of gain or in terms of cost, taking into account as well the operational cost. And again, there is not one size that fits all, so there will be different trade-offs. And one thing that is exciting also here is to see how we are going to balance between all these different factors, right? But now if you take a step back and you talk a little bit more about the long-term vision, what we see is kind of a modular data layout optimization engine, something that can reason about layout holistically and adapt as your workloads change and depending on your needs, right? That means supporting maybe things like auto-sort, auto-partition, auto-index, you name it, right? Each working towards improving performance or cost under specific constraints. And obviously it needs to be extensible and interoperable with existing infrastructure. We talk in the context of Openhouse, right? And that's how we implemented things initially, but there is no reason that this type of tooling needs to be associated with a single control plane or a single catalog, right? We could develop this and integrate it with different of them. But now, getting there won't be easy. There are still some big open problems, as you can see. To name a few, how do you schedule layout optimizations without disrupting workloads? That's something that we didn't talk at all today, and it's something that we have observed and that it is important. How do you coordinate compaction and grade policies across engines? How do you build better cost models that actually reflect the workload realities? So you could see there that the cost model that was being used at linking has proved very effective, as you can see. But when we studied it in a little bit more of detail, we saw some discrepancies between what the model was returning versus, for instance, what the cost to run the actual compaction was, right? So I think there is room for improvement there. And can we should we start integrating also some learning-based strategies that adapt over time? So these are kind of problems that, again, shouldn't be solved over and over again by every vendor, infra team, research group. And the call here is, why don't we build it together, right? So if this resonates with you, we'd love to connect. So come chat with us after the talk or reach out directly. And that's all. Thank you. We also have more details about Autocomp in a paper that will be presented as SIGMOD later this year. So if you want some more details, you can go and check it. Thank you very much.
I actually have 2 questions, if I may. So one of them is basically you've shown some graphs on how to put it, your improvements and the costs or the growth, to be clear, right? They appears to be both kind of rising linearly, right? And my assumption would be that spending so much time on the engine and its evolution, at some point you would like it to be in a way disconnected, right? So your improvements and effectiveness should be in a way better than your growth, right? So this is kind of one thing that I noticed. And the other one is kind of, so if you running Kmax constantly, how are you avoiding a problem of the engine basically picking up with the same budget, right? Even though you might do recalculations based on the total amount of the data you store for this particular budget, but how are you avoiding cases of picking the same K things over and over again?
Yeah.
So, thank you.
Yeah. Great question. So to answer your first question, I guess the linear growth is expected as the deployment size is going to grow. We are also going to see the number of file counts are going to grow. At what rate is the real question here, right? So before we were, as I pointed out, before the rate of growth on file count was much faster than the deployment size, but now it's much slower. So that's where I think that we have bent the curve on the growth first, and then now we are growing slower than before. So I think the rate is the differentiating factor between before and after. I think the second point is a really good point. There are observations in our deployment as well where we see the same table being picked. Now you could argue that, hey, we are doing a right job, we are showing all these great metrics, but in reality, what should we do? Should we go tell the writer that, hey, why don't you optimize your right job and we don't run into that scenario? That, or we tune our algorithm in such a way that we have some kind of memory built into our top K selection process where we'll try to see that table maybe after a week or something like that. So I think that is something that we will want to iterate. We haven't looked at it, but you are absolutely right. We are seeing some top 2 or 3 tables come very often, the same tables.
It's a constant trade-off, right? So even if you have a feedback cycle, if rewriting or eliminating small files in a particular table give you the same gain, you're not even exploring the
Other
other
tables,
right?
correct.
And that's the feedback loop.
Correct.
And then you come, whether you do the randomization or something, that's always a trade-off.
It's a trade-off, absolutely.
I think one other point is, or a few of them, but one is also the granularity at which you are selecting this table. And when I mean granularity, I don't mean table and partition right now, but how you group them together. So you could think like, you have some different units, right? And then you're gonna have tables allocated to each of them, right? And you're gonna have a budget per unit. Now, it's true that the same issue, you will hit it per unit, but you can kind of minimize that issue because now you allocate for sure certain budget to a certain group of tables. Yeah, yeah,
Yeah.
yeah, that's right.
In fact, we have some weights given, and the interesting part here is as you add more optimization objectives to this equation, it may happen that maybe that table doesn't get picked next time. If we add, let's say, query performance gain as an optimization objective, we'll pick a table that is suffering on the queries higher than the other table. So it's
Have you done any other type of optimizations during compaction, like changing the parquet row group size or anything else? Because it sounds like from the compaction, it's just simply going from small files to bigger files. Yeah. Is there more than that you're doing behind the scenes that we can learn from?
not right now. We are just using the plain Parquet compaction which is merging to multiple files. But we have talked about doing sorting during that compaction, but that still doesn't change the Parquet row groups or anything of that sort. Yeah.
One other thing to add, and that we didn't talk about today, but in the paper there are a little bit of details. There are certain constants or parameters that affect all this, right? Like what you are describing. And one thing that we started experimenting with was another project that we've developed at GSL that is called MLOS, so machine learning open source, that it's about auto-tuning of some of these parameters. And we did some experimentation where we do tune some parameters. In particular, we're focusing on auto-compaction parameters because there are parameters under the hood there, but you could also extend it to the engines as well. So yeah, that's something that we look a little bit into and we plan to look into in the future. Yeah.
How do you deal, well, first off, when you're approaching this, I feel like you're assuming a table has been set up in an optimal manner before you're looking at the compaction. So how do you deal with, let's say, tables that are over partitioned where you run compaction, you're still going to have, say, 500,000 files in a 10 megabyte table because there's too many partition columns, for example?
One of the things that Jesus touched upon is some of the overestimation that we are doing right now in our cost formulation and benefit formulation. So when we do compaction at a table level, we don't look at partition granularity. And when you do that, you look at the whole table scope, but then you know that you cannot compact files that cross partitions. And that's where we observed that there is this overestimation coming from that. Now moving from a table scope to a table partition scope where we are ranking table partitions should allow us to get a better granularity in better estimation that we do in terms of like computing the traits. You want to add anything?
Yeah, just, I mean, that's a very valid point. I think one other thing is also that, as you collect some of this information, that telemetry, you can kind of, it's about looking holistically at the workload, right? So, you can push this kind of knowledge to your producers. Then they can do different things with it. But yeah, it's about looking, I think, holistically at the whole thing. Yeah.
Exactly. And some of the work that we want to do next is exactly that, like, are we over partitioned or are we under partitioned, that kind of thing. And in the roadmap, Jesus talked about there is something called Autopart. As part of that, we are looking at what is the cardinality of your column, what is the number of non-distinct values you have in a column. Based on that, we can come up with these strategies that this table should be partitioned by a certain column, or this table should be sorted by a certain other column. So that's future work.
So I think you briefly touched on this also, but what I didn't see was relying on the query characteristics to to figure out what you should do with the table. So for example, if a table is just being written all the time, but not really queried, then why you should pick it up for compaction,
Exactly.
right? And on a similar note, right? I mean, going forward, as you can see, every single table is going to have its own custom compaction strategy, or some other way that will have to look at a querying, query characteristics, if it's filtering one particular column, etc., etc. So do you expect, folks who are, let's say, operating the platform to go set those custom policies on those, or will the system? Do you see a world where system can just do it magically?
So the goal is the system should be able to do it magically. How we get there is, I think, the point. But you touched on upon an optimization objective that we want to consider in future, which is how do you maximize query performance gains. We haven't included that in Autocomp's first version, but what that would mean is now you're trading off your multiple objectives. One of the objectives that we discussed was maximizing file count reduction. The other would be something like maximizing file scan, like reducing the file scan during your queries, right? So once you have all these optimization objectives like together, so often they are conflicting objectives, right? Like you pointed out, you don't query that table, and that there was one, like table D was never queried. Should you pick it or not? Today we will pick it. But tomorrow when we add file scan objective as an for optimization, we will not, because it will be ranking that table much lower. That allows us to get that dynamicity, if you will, in our picking. You want to add anything? Yeah, Tom.
Thank you. So like the point I wanted to touch upon was like when we're writing data, so there's a job that's initially writing data, then you're actually looking at various observations from that and the read consumptions to then run an optimization job, right? Like compaction in this case. Are there patterns you're seeing wherein you want to push some of the compaction optimization into the right job itself to begin with, saying that, hey, you know what, so that we either minimize the amount of work we do here? Like, I was just curious to see what patterns, if any, you've seen there.
This is something you looked at.
Yeah, that's something, again, we couldn't cover today, but in the paper you have some information about this. The idea is that this framework that we're describing, right, you can use it in multiple ways. So you will be able to run it on a schedule, and that's what we're talking about, and that's how it is run at LinkedIn. You could also maybe put it into one of your post-grade hook, right, in Spark. And then you would make same type of decision whether you want to compact after grade or not. And we talk a little bit about that part. There are questions there whether then in that when you do that, whether you're going to be looking at the whole world at that point, or are you going to be making a slightly different, more local decision? That's something that you can implement one way or another. But again, the idea was that the whole framework, you can use it in different ways. That was the vision. Yeah, and yeah.
I would argue that so part of the data that you're getting might not be true, in the sense that how would you validate the whereas the query is just slow because of the data modeling, inefficient querying, or because of the underlying data layout or so, right? So whatever you're getting as an input, it should be weighted and validated as well, right? So you should have a strong signals on whatever comes to you is actually correct in this sense. So this is basically back to the previous question.
You want to take that one?
Yeah, so we agree with you. So it's a hard problem. That's why also we focus on the other one first. But indeed, there are many different aspects that will influence query execution, right? And it's not even only about the scan itself. So yeah.
When doing compaction, did you all see a hit in the read heavy tables? Like, did you all kind of schedule it such a way that the compaction is not hitting performance of reads that are happening at the same time?
So yeah, that's a good question. So we haven't really scheduled the compaction like right now we haven't given enough thought to that. We have a particular schedule at which Autocomp runs, but with Iceberg, given that we have the snapshot isolation in Iceberg, like we are kind of like a particular read is pinned to a snapshot in Iceberg. So it's very predictable in the kind of like what data files it will touch. So if a compaction is running concurrently with an incoming read, then they are isolated from each other. So we shouldn't expect any interference because of compaction. Now, the impact on storage, impacting the rest of the world, I think that's a different thing, and that's why we should be like a little mindful about when we run compaction. Where it really impacts, and Jesus touched on it, was compaction commits conflicting with writer commits. That kind of like is a big issue, especially if you have a table that you're compacting that is getting like a very like low latency commits, like 5-minute commits.
Yeah, and that is something that we could, by the way, reproduce and explore very easily with the synthetic benchmark that I was describing. Because you are basically, we're being very aggressive on the compaction side, and then you could see some of the trickle inserts conflicting basically with that compaction. So yeah. I mean, right now we don't. Like Sumit was saying.
I can add to that. So generally, the way we observe our workloads is they usually have like a daily granularity or an hourly granularity. We haven't enabled compaction on the tables that have 5-minute commits yet. But one of the things that we are trying to think of is to the point that Pawan was making, like how do you do this kind of a compaction as part of the right job? So we're trying to see if we can embed that compaction algorithm as part of the ingestion pipeline without really compromising on the SLAs for the ingestion. But that's still work in progress.
This is more of a fundamental question around compaction in Iceberg. When you're, let's say, compacting 10 files into one file, do the 10 files are deleted right away once they are compacted, or are they kept around for X amount of time until like a maintenance job kicks in and then deletes the file? So if is that the case, or if the files stick around for some time, like then you have actually some growth initially and then eventually like a cleanup.
Exactly.
So that's my
That definitely. So yeah, you're absolutely right. Iceberg has its own write amplification, which kind of we touched base on. So it doesn't need a compaction job to result in a write amplification. If you are trying to update a partition using copy on write, you will have like the old data and also the new data for a certain period of time until you have a system which is promptly expiring snapshots, deleting orphan files and stuff like that. So yeah, we will experience that trend. But in our measurements that we see is usually a fixed cost of amplification if you are doing a really good job at making sure all your maintenance runs on schedule.
Okay.
Thank you
you
so
everyone
much
for being here, and thank you for